I'm working with
Okay, so we'll try to finish thermal cooling and hopefully get into mixtures. So we set up the differential equation for Newton's law of cooling, and the idea was that if you have some object that's in a room that's not the same temperature, either colder or like your coffee is in an air-conditioned room, so your room is colder than the coffee, your coffee will cool down, but it's going to cool down at a rate that is proportional to how big the difference is between the coffee and the room. So it'll cool down faster in the freezer than it will cool down in an air-conditioned room. And so the way you would write that is the rate of change of the temperature of the object, capital T being temperature of the object, and little t being the time. This rate will be proportional to the difference between the ambient temperature and the temperature of the object. And the difference needed to be written this way. It had to be Q naught minus T, because if you didn't have that, then we discovered that you'd have weird situations where your coffee is getting hotter in a freezer or air-conditioned room. So we could do the final check right here, where we said, let's look at the case where you have your temperature of your object is, this one was greater than zero, Q naught, but let's say if it's less than Q naught, which means that it's like iced coffee. Your temperature of your coffee is less than the temperature of the room, so it's cold. The drink is cold. Then that means that the right-hand side, which is Q naught minus T, would be, instead of less than zero, it would be greater than zero, because the T is less than Q naught. So the Q naught would be bigger than the T. And that means that since you're saying that your dt over dt is proportional to this, that means that your change in temperature of your iced coffee should be going up, because basically you have the right-hand side is positive. So that means, so it's like saying this Q naught minus T is positive, K is positive, then dut over dt is positive. And this makes sense because if you have iced coffee, which means that your T, which is the object temperature of your object, is less than your surrounding temperature, you would expect the temperature of your object to go up. And so your iced coffee will reach room temperature, get warmer and bit warmer and reach room temperature. So this verifies this green box does indeed describe the correct differential equation for the Newton's law of cooling or heating. And we can use this to solve all kinds of questions. So there are some assumptions you could make. Let's say, so I'll just say here, K is a proportionality constant. We're going to assume K is greater than zero, because if we had K is less than, if you had K is negative, then it'll mess up all this logic here, because this, physics that says that the temperature of your object being hotter than the room temperature causes your temperature of the object to go down, is going to mess up if you had a K that's actually negative. So you need to have this, this is proportionality constant. So you can write this in standard form. So let's just do that. So we'll just say this dt over dt is equal to K Q naught minus KT. What's our unknown? Our unknown is our capital T. So you could shove that onto the left-hand side and you get positive KT equals KQ naught. This is the so-called standard form. And you can assume that, so why don't we make some assumptions to solve this? So Q naught, K is already a constant, so we know those are constants. So that means that because K is a constant, so this is a constant too. I'll just do it this way. So the K's are both constants. So because it's a constant, you can do the method of undetermined coefficients, in particular because this K in front of the T is a constant coefficient. So we could use the method of undetermined coefficients. It's going to depend on what our Q naught is, though. If your Q naught was like a polynomial, or if your Q naught was like a sinusoidal or an exponential, that's going to determine how you build the particular solution in general. But why don't we just, for now, make the assumption that your ambient room temperature, surrounding temperature, is also a constant. Let's assume, say it's a constant. It may not always be a constant. You may have a surrounding temperature that's not constant. So this is like, say, so this means that your ambient temp is kept constant. If you had that, then you have a right-hand side that's constant because K is a constant and Q naught is a constant. So you can build the particular solution, which is capital T little of P is equal to just a constant A, right? Remember, that's the form for when you have a constant forcing function. So you plug this into the differential equation. That means that your dt over dt, the d capital T over d little t, is 0. Plus, this is just going to be k times a is equal to k times q naught, which means that your a is equal to q naught because you just divide both sides by k. So that will be a particular solution, and your full solution will just be built off of this particular solution, which is the q naught that we just got, which I'll make it purple to make it like the particular solution, plus the homogeneous solution, which I'll use, I guess orange, is going to be easy because you read off from this differential equation, right? This is the standard form already right here. It has a k that's positive in the front, so it'd be c e to the negative kt. And so you have your particular and your homogeneous solutions. This is your homogeneous solution. Well, I'll call it capital TH. And then this is your particular solution, which is your capital TP. And this is your general solution to your to this problem. Assuming we're making a big assumption, we're assuming this Q naught is constant. That's the only way we were able to say that the particular solution form was also a constant A. So this is the general. Now, suppose you also had some initial conditions. So suppose we had that there was an initial condition. Suppose that the initial temperature of the object, so T capital T of 0, is some initial temperature T naught. We usually use that in the past where we had initial population P of 0 is equal to P naught. Same idea, initial temperature is T naught. Then if you plug this into your, suppose you had this, what does this mean? This means that your capital T of T, this left-hand side, this black thing, is T naught whenever your T, which is this little t, is equal to 0. So e raised to negative k times 0, which is just 1. So then you just get that c has to equal. So the idea is you plug in an initial condition to be able to find what that c is going to be T naught minus C naught, Q naught. Because this is just a 1, so it's just going to be T naught minus C. So that's the C. And once you plug that C into this, right, into here, then you get your actual solution for the temperature as a function of time. If you have an initial condition like this, and you also have that your temperature of your ambient surroundings is kept constant the whole time. So this is going to be the solution for if you, I'll just say here, only for Q naught constant, right? Because we use this right here, and that was required. We needed to assume this to be able to build a particular solution of this form. So this is like, of course, if this Q naught was a sinusoidal or polynomial something, then this T of P wouldn't be just A, it'll be like A times cosine of T plus sine of AB times sine of T, or it could be polynomial, which is going to have like A naught plus A1T plus, so if you can assume that you're keeping your surrounding temperature fixed, then all of this works and you'll get that this is the solution given also this initial condition. And not all situations will be like this, so you want to make sure that you are careful about that. So, yes.
So in other words, when you say only when Q naught is constant, only when the surrounding temperature.
Yes, yeah, when the surrounding temperature is constant. Okay, so we'll use this first one. This first case we'll do an example of right now. Suppose the room temperature in your office is 70 degrees, and we're just going to assume that it's fixed at 70 degrees, and you have like some thermostat that's like setting it fixed to 70 degrees. Experience has taught you that the temperature of the cup of coffee that you have in your office will drop from 120 Fahrenheit to 120 degrees Fahrenheit to 100 Fahrenheit in 10 minutes. What will be the temperature of the cup of coffee after 20 minutes? So here, we're just going to assume that your office, Q naught, is the temperature of your office is 70, and it's going to be constant. Like basically most rooms are, climate controlled, so it's not like getting hotter or colder, it's just going to stay at 70 degrees. And that's going to be, so we can build a differential equation, right? So if you wanted to, you could go back to the original differential equation, which is this thing right here, this idea that your temperature of your object, which is your coffee, is going to be, rate of change of your coffee is proportional to your ambient temperature minus your temperature. And this, if you wrote in standard form, would have been this. You have the K times negative T, which is going to give you positive KT on this side, and you have K Q naught on this side. And for our problem, we are going to say that this Q naught is 70 and it's going to stay constant. So because of that, our differential equation will end up being dt over dt plus kt is equal to 70. Okay. And you can use, so we solved this differential equation before, you can use this result that we got before here. And so if you wanted to write the differential equation, this would be the differential equation. But we already know the solution will be like this. But with our Q naughts, I'll just say that the solution will be like this, but the Q naughts will be equal to 70 plus, it's our initial. So we'll make, so let's just say that I'll underline that in blue, and then say from this, we can say that our T naught is equal to 120. That's your initial temperature. And then in 10 minutes, it will be 100. So we have two things. This is like our initial temperature. So that means that this is like our T naught. So we'll use 120 minus, again, Q naught is 70, e to the negative KT. So this is the actual with all the information plugged in. And we're going to have to find this K. So what do we want? Let's just underline what's the temperature of the coffee after 20 minutes. What does that mean? That means that we want to find T of 20. We know T of 0 is 120. We know T of 10 is 100. But what is it at 20 minutes? But we're not quite able to just plug in little t is equal to 20 in this because we got to find this K. And you're going to use this information. They usually give you enough information to fit the proportionality constant. Just like with like the population growth, or, it was like you observe that after 10 minutes, this much bacteria was there. So there was always some kind of condition that allowed us to compute the rate term. So this orange box here just says that your temperature is 100 whenever your, so I'll just say that 120 minus 70 is just 50, e to the negative k times 10. And you can subtract both sides by, so let me just say that this is coming from this condition. Gives you this. And then you subtract both sides by 70, you get 30 is equal to 50 e to the negative 10k. And then you can divide both sides by 50, and you get 3 over 5. Just gonna simplify the 30 over 50, e to the negative 10k. You can take the ln. Ln of 3 over 5 is equal to negative 10k. Therefore, your k is equal to ln of 3 over 5 over, or I guess negative ln of 3 over 5 over 10. This is still positive because ln of 3 over 5 is negative. But now that we found the k, what is it that we want? We wanted to find this, which is T of 20. T of 20 is what we wanted to find. So we'll just take the expression that we'll get once we plug in this k. So it'd be T of 20 would have been essentially this thing, but with the k being this. So it would have been like basically there's a negative and a negative, and then we're interested in computing when it was so I'll just do t times it's going to be ln well, I'll just do this 1 over 10. So this is a t times 1 over 10 times ln of 3 over 5. There's a negative here and a negative here, so there's no more negatives after those cancel out. And what do we want? We want to find what this is equal to when t is equal to 20. So we'll just say that we're plugging in 20 into this t. That's just an exercise in typing in your calculator, because this is all just numbers. And you'll get that T of 20 is approximately 88 degrees Fahrenheit. So this was a case where your temperature of the room is kept constant. So you can use this result right here that we had gotten before, because this was solving it in general, where this Q naught is the temperature of your surrounding. And in our case, the Q naught was 70. So all the Q naughts became 70. And then, you might have some initial condition. In our case, it was 120 was the initial temperature of the coffee. And so that's it. Those are the only things you can plug in. The K stays, and of course the T is there. The K, you have to be able to find by using another piece of information they give you, because you need to fit the proportionality constant to the data that they have, which is that if you have coffee that's 120 degrees Fahrenheit initially, after 10 minutes in this room, it will go down to 100. And that'll give you your K. But the question they want is how much now do you predict the temperature of the coffee would be another 10 minutes later at 20. And this, I'll just underline this in red. This right here is a function of T. right? This is like all this stuff with a function with a t in it. That is actually going to give you this graph, this red graph, right? So you see this red graph. It's an exponential decay because the ln of 3/5 is actually negative. And so it'd be e raised to something that's actually negative times t. And so you have an exponential decay. And what's happening is that it does actually look, the model is what we said, and needed to have at t equals 0, it needed to have 120 degrees. And then after 10 minutes, it's 100 degrees. And then after 20 minutes, it's 88 degrees. And you can, put a plug in 30 minutes, 50 minutes, 60 minutes, 70 minutes, you'll get like some numbers that are going to be towards the right of this red graph. Now, this is decaying, but never going below this blue dotted line. And why would that be? Yeah, it's the ambient temperature. So this solution, this red underlying thing, is going to be an exponential decay with an asymptote at 70. It will never go below that because the coffee is starting hotter and it'll get cooler and it cools down slower and slower, but it will never get cooler than the actual room, right? So that would be weird if it just kept going cooler. And you can clearly see from this graph that the rate that it goes down is faster initially. So if you look at like the slope of this graph right here, it's really steep initially, and then it's less steep and less steep. So if you thought about your dt over d capital T over d little t, it's getting smaller and smaller as you go further, is because your difference between your surrounding temperature and temperature of the object is getting smaller and smaller. And because we said that the physics of this is going to be modeled by the rate of change of temperature being proportional to the difference between the object and the temperature of the surroundings, we expect that as the temperature of the object and the surrounding gets smaller and smaller, the slope of this decay, it's still going to go down, but it's going to go down at a slower rate. And so it's going to be less and less steep. And so it's just saying that it's getting cooler, but much faster initially. And then as time goes on, it's still cooling, but it's cooling very slowly because it's already very close to the temperature of the surrounding. Now, that is the case where we had constant temperature. Suppose now instead you have some instrument that has an initial temperature of 40 degrees, is placed in a room whose temperature is initially 20 degrees, but for the next 5 hours, the room temperature in the room is actually being increased, and it's increased by 10 degrees every hour. So the Q naught, which is the ambient temperature, is not a constant. It'll be modeled by 20 plus 10T, 20 being the initial temperature, plus 10T to reflect the fact that it's being increased by 10 degrees every hour. Let's just save ourselves the trouble of finding K. So I'll just say from prior experience, you've done some measurement and figured out that K is actually equal to 1. Find the function capital T that describes how the temperature of the instrument changes with time. I guess I should have also mentioned that this K right here is like the proportionality constant. The rate of change of the temperature is going to be proportional to the difference between the temperature of the surrounding and the temperature of the object. But how sensitive is it to the difference in the temperature of the surrounding and the temperature of the object is going to be this K. And so this K could be thought of as like the heat conductivity of your object. So this is like your heat conductivity, how well it responds to your difference in the temperature of the surroundings with the objects. So let's say this person's done some experiments and found out that like the heat conductivity is just 1, just to make our life easier. Then I'm going to tell you right away that this right here, this formula that we got, I'll just take the whole thing. Remember, this right here was only for when Q naught is constant. So you cannot use this in this problem. So remember, this was only for Q naught is constant. So therefore, you can't use this. So you have to go back and remember that your differential equation for the temperature is going to be equal to K times the, ambient temperature minus the ambient temperature minus the object temperature, which if you written in standard form will be plus KT is equal to KQ naught. You'll have to go back to this, and in our problem right now, our Q naught is not constant. It's actually going to equal 20 plus 10T. And we also know that the K is given to us, it's equal to 1. So our actual differential equation is dt is plus t, because k is 1, is equal to 20 plus 10t. This is going to be the differential equation that we'll have to use. And the solution to this will not look like this because this solution was when Q naught was constant. Here, and because we assumed Q naught was constant back then, our T of P particular solution was also a constant. But when you have a differential equation of this form where Q naught is not a constant, but like a polynomial, our T of P is now all going to be a polynomial. So it's going to be A naught plus A1T. And you're going to, okay, so I'll just say this is a degree 1 polynomial. So you're going to plug this in to the differential equation. Your derivative term, dt over dt, will just be A1. That goes away and just has this. Plus, you're just plugging in this whole thing into your t. And this is going to equal your 20 plus 10t. And you're going to match terms. So you're just going to say that this A1 has to equal basically 10. So you'll have that this is going to give us that A1 equals 10. Then you need to have these two, A1 and A naught has to equal 20. We already know that A1 is 10, so it'll be 10 plus A naught has to equal 20. Which means that A naught is equal to 10 as well. So we got this, and we got this, and so we have our particular solution will end up being, I'll just say therefore, our particular solution is just going to be A naught is 10 plus A1 is also 10. So this will be our particular solution. And you can build a general solution, again, by just saying that our T of T is going to equal our particular solution, which is this, plus the homogeneous solution, which is just reading off the, there's a plus capital T here, so the coefficient in front of that was 1, so it's going to be negative K, well, negative T. K is just 1, so that's going to be negative T, and that's our homogeneous solution. And this is our particular solution. So this is our general solution. But if we want to know the temperature as a function of time and want to say we want to graph it, we can't have this C just be just C. We need to find what that C is. So it gives us that the initial temperature of the object is 40. So we have an initial condition, which says that our temperature of the object initially is 40. So let's use that. If we are going to say that the initial temperature of the object is 40, this is like saying 40 equals 10 plus 10 times 0. plus C times E raised to the 0, because negative 0 is 0. And this is like saying that C is equal to 10 times 0 is 0, so it'd just be 40 minus 10, which is 30. So if you plug that into here, then we do get an actual formula for the temperature as a function of time. It's going to be T of T is equal to the 10 plus 10T plus C. No, C is 30 now, so E to the negative T. And this is looking not, it doesn't look like this, because what happens with this one is that this one has some kind of term multiplied by e to the negative t with only a constant term in front, but really this one needed to have had a linear term. There's no linear term in this. So you really can't use this one, because this one was the solution for assuming Q naught is a constant. So you have to go back to the original differential equation, which is really this idea that the rate of change of the temperature is proportional to the difference between your surrounding and your object. And in this case, the temperature of your surrounding, Q naught, is not a constant, it's a polynomial. So you'll have a right-hand side forcing function that's a degree 1 polynomial. So you build your particular solution this way, and then you tack on your homogeneous, and that is giving you a linear term, 10 times t, that doesn't show up in this one, because this one just assumed that your ambient temperature is a constant. This one, because of the linear term here, is not just going to be an exponential decay to a flat. It's going to have some term that grows linearly as a function of time, as time progresses. And so if you plotted this, I'll use red. If you plotted this one right here, you will get this plot right here, which is this red line right here. And it looks much different than this one, because this one flatted out. This one flatted out because basically you have an exponential decay term plus a 70. And in the infinite limit, in the t going off to infinity, given that ln of 3 over 5 is a negative number, you have this term goes to 0, and you just have 70 left. And that's why it went down this way. This one right here, as t goes to infinity, the 30 times e to the negative t will vanish, because you're making the t go away, and you would be left with 10 plus 10t. So in the limit of infinite time, or if you go on forever, further in time, it's going to behave like 10 plus 10t, versus this one is going to behave like 70 as you go infinite in time. And the reason is because the temperature of the surroundings, so the temperature of the room, is actually this blue. So I'll just underline this and say this Q naught right here, this 20 times 10 to the 10 times T, that's our blue dotted line. You can see here that initially it has a 20, and then this is a slope of 10. You can trust me on that. So the temperature of the room is being increased. What's happening here is that your object is initially hotter than the room, because it's saying that the initial temperature of the instrument is 70, placed in a room whose temperature is 20. So that's why this red graph is higher than the blue graph initially. So what is it going to do? It's going to cool down, right, to become like what the temperature of the room is. But the temperature of the room is being increased. There's going to be a moment where they're both going to equal the same temperature, because it's like your object is hot, your room is cold, your object's going to cool down, your room is heating up. There's going to be a moment when they're both the same temperature. Then the temperature of the room just keeps growing. So the object is going to feel like it's cooling down, but then it's going to react to the fact that the temperature of the room is increasing. And so that's why it's like, okay, well, I was cooling down because the room was colder than me. I attained the same temperature as the room, but wait, the room looks like it's heating up. And so now the object is also going to heat up with the room, but it's going to lag because the room heats up first, and then the object is going to react and heat up with it. So it's going to follow the upward trend, but with a delay. That's why the blue graph is actually higher the whole time. You know, after they've reached the same temperature for a split second, all time after that, the room is actually always a little bit hotter than the object because the object is just catching up to the room. The object is not, it's just reacting to the room, the temperature of the room. So that's why this looks like this. And it'll always follow this forever if we're assuming that the room is always going to get hotter and hotter. Does that make sense? Okay. So the key point is you can't use this formula here. You have to go back to the original differential equation, and your Q naught is, in this case, a polynomial. You may have a Q naught that's not a polynomial. It could be a sinusoidal, which is common for like if you're trying to model the temperature of like the air outside, because it gets hotter during the afternoon, gets cooler in the evening, and then like coolest during the midnight around in the really, really late night, and then gets back up. And so you could model the temperature of your surrounding air over a 24-hour period relatively well using a sinusoidal function. And so all of those cases, you have to go back to the original differential equation and then plug in the correct forcing function. And if it's not a constant, then you can't use this general formula right here. You'll have to just solve directly using the differential equation that we have originally. So that's the Newton's law of cooling. There's one last application, which is mixture problems. And this also could be modeled using first order equations. And this will be the last example, and it can be kind of challenging. So hopefully I could set it up enough in the next 10 minutes so we can just do problems next time and not have to worry about why the equations look the way they do. For this one, let QT, which is so it's confusing, but it's capital Q again, but it's not representing temperature at all. This QT, let that be the amount of some species in a tank. So like it could be concentration of some pollutant, or it could be salt that's being dissolved. And so we're going to say Q of T is the amount of some species, and we're going to say like that's going to be it's the mass. So amount, let's just say amount equals mass of some species. So, suppose it's in grams. It could be kilograms, it could be pounds, but just some mass of some species in a tank that's well mixed. The fundamental physics for this is going to be the rate of change of the amount of your pollutant is going to be how much your inflow rate of pollutant minus your outflow rate of pollutant. So again, we said that Q is grams. Let's say T is seconds. Then dQ over dt will be grams per second. And so there's some flow of grams per second of pollutant that's changing in this tank. And how many, the rate of change of your amount of pollutant in this tank is going to depend on the rate of pollutant coming in minus the rate coming out, right? This is like the law of conservation of matter. So these are also grams per second. So like if I said that I am pumping in sodium chloride at a rate of 5 grams per second, and I'm pumping out at a rate of 3 grams per second. What's the net change of sodium chloride in my tank? It would be 5 minus 3. Equals 2. You're going to get a net gain, right? Because you're pumping in 5 grams per second and you're pumping out 3 grams per second. And so your net gain of salt in your tank will be 2 grams per second. And if you kept doing that, then it'll be like there'll be 4 grams the next second, and then 6 grams, because you're adding basically a net gain of 2 grams per second. This is like conservation of matter. It's like supposed to be like what you would expect, by common sense, that if you're pumping in 5 grams per second and pumping out 3 grams per second, then the rate of change of Q in the tank will be 2 grams per second. And that's what it's saying here. It's like, let's say your inflow rate is 5 grams, your outflow rate is 3 grams per second, then your overall rate of change of Q in this well-mixed tank will be 2 grams per second. So this is the equation we're going to use. It's just the conservation of matter. So let's consider a tank that's filled with 100 cubic meters of water. The water contains salt at a concentration of 1 grams per meter cubed. So that's how much the salt concentration of the tank initially. Then you're pumping in less salty water. So you're pumping in diluted water. The water that's being pumped in has a salt concentration of 1/10 of your original concentration in your tank. And so that's like 0.1 grams per meter cubed. Is pumped into a well-mixed tank at a rate of 5 meters cubed per second. Then you have water flowing out of the tank through an outflow valve. It's being pumped out at the same rate you're pumping in water. So that means you're trying to keep the tank not like you don't want a tank to blow up. So you just have like 100 cubic meters in the tank. You're just pumping in 5 cubic meters per second of diluted water, but whatever, and then it's being well mixed. And then whatever rate you're pumping in, you're also pumping out. And so it'd be 5 cubic meters per second being pumped out. Determine the amount of salt, Q of T, and the concentration of salts, little c of T, in the tank as a function of time. Okay, so let's just write some stuff we know about this problem. We know that this arrow is pointing in here, so it's saying that you have an inflow rate. You're pumping in, first of all, you're pumping in water that's less concentrated, so it's going to be 0.1 grams per meter cubed. This is concentration because concentration is mass over volume. And then you're pumping in at a rate of 5 cubic meters per second. So that's our like pumping in. So this is like our what's going into the tank. Now what's going out of the tank again is going to be pumped out at the same rate that water is pumped in. So the 5 cubic meters per second is going to be kept the same. So you're not having any net change in volume in this tank. The water coming in is 0.1 grams per meter cubed. I'll just say here initially your concentration of your tank here is, I'll just say C of 0. So little c is concentration. Little c of 0 is equal to 1 grams per meter cubed. Right? This is just mass per over volume. This is concentration. So clearly the tank initially, that's why it's got a C of 0 here. Initially, it has a higher concentration than obviously the water that's being pumped in. Now, this water that's being pumped in is fixed at this rate, at this concentration. The water then it comes in, let's assume that's well mixed. Otherwise we can't, we can't assume the model breaks down assuming that this is well mixed or uniform concentration. And you're pumping water out at 5 cubic meters per second. Now, while we know that the water being pumped in is 0.1 grams per meter second, what do we know about the water being pumped out? Or do we know anything about the water being pumped out? It's hard to tell, right? Do you think that the water being pumped out would be also 0.1 grams per meter cubed? No, because you're putting that into a tank that's more concentrated. But it's probably not 1 grams per meter cubed too, because it had been diluted by the fact that you're pumping in water that's less concentrated. And so the best thing you can say is that the water coming out is some unknown concentration, C of T, grams per meter cubed. This is actually like something we don't know about this problem. Is like we're going to have water pumped in that's fixed to this concentration. It's going to get mixed, and who knows what the concentration is that's getting pumped out. The water that's being pumped out is going to be whatever concentration this tank. So if C of T is the salt concentration in the tank as a function of time, then that's changing with time. And the water that's coming out would be whatever concentration of that tank is at that moment will be the concentration that's being pumped out. And so we have all this information, but the inflow rate, we're modeling this as the rate of change of mass Q of your pollutant or your salt. So these are grams per meter cube. This is meter cube per second. How would I get grams per second out of this? So if you look at your inflow rate is in grams per second because we're trying to find how much in grams is Q changing with respect to time seconds. How would we get that? If we know that your concentration is 0.1 grams per meter cubed and you're pumping in at 5 cubic meters per second, how would you be able to tell the rate grams per second? You just multiply them. So you can just say that you have here flow of volume of water coming in is 5 cubic meters per second, multiplied by concentration of pollutant flowing in, 0.1 grams per meter cubed. And then if you do that, the units will cancel and you'll end up getting that. This means that you're pumping in water, you're pumping in salt at a rate of 0.5 grams per second. This is like saying I have a concentration of 0.1 grams per meter cubed, and then I'm pumping at a rate of 5 cubic meters per second. That means that in every cubic meter, there's 0.1 grams. So there's 5 of those being pumped in per second. So that means you have 0.5 grams of pollutant coming in per second. And that's going to equal this right here is 0.5. The outflow rate is going to be the same idea. It's going to be just these two multiplied together. So it's going to be equal to 5 cubic meters per second plus C of T grams per cubic meters. And so it'll be 5 times C of T. That one looks weirder because the C of T is unknown, but that would go into here. And we'll pick up from there and do the rest of this. So.